In 1935, over a quiet conversation over tea at the Institute for Advanced Study, Albert Einstein set out to prove that quantum mechanics was incomplete. Instead, he uncovered what physicists now call the Einstein-Podolsky-Rosen paradox, the EPR paradox. The claim that two particles, once joined, can share a single fate across any distance, agreeing in an instant, though nothing you do to one can send a single message to the other. Einstein called it spooky action at a distance, and he meant it as an insult. He was trying to expose a flaw. What he found was the deepest and strangest connection in nature. Stay with me, and you will understand why this one paradox, argued out between Einstein and Niels Bohr, sharpened by Erwin Schrödinger, and finally settled by John Stewart Bell, quietly breaks the intuition that things only touch when something crosses the space between them. Here is the tension in plain words. Quantum entanglement links two particles so that measuring one instantly fixes the state of the other, whether they sit a meter apart or 1,200 kilometers apart, as they did when China's Mityuus satellite beamed entangled photons to mountaintop stations in 2017. The correlation is perfect, immediate, and real. And yet, you cannot use it to signal, not one bit. The universe connects everything instantly, but signals cannot cross that connection. By the time the screen goes dark, you will understand what entanglement actually is, why Einstein believed it proved quantum theory unfinished, how Bell turned a philosophical dispute into a number you can measure, what the loophole-free experiments of 2015 and the cosmic tests of 2018 truly showed, and why the correlation carries no message. If you find value in explorations like this, the subscribe button quietly helps these deep dives reach more curious minds. So, here is where it begins. To understand what Einstein objected to, you have to understand what he was defending. He was defending a picture of the world that seems too obvious to state. That things have properties whether or not anyone looks at them, and that nothing here can instantly affect something over there. Physicists give these two commitments names. The first is realism, the idea that a particle has a definite position, a definite spin, a definite state, independent of measurement. The second is locality, the principle that an object is influenced only by its immediate surroundings, and that any influence between separated objects must travel through the space between them, at or below the speed of light. Together, realism and locality form what we might call local realism. And for most of the history of physics, it was assumed, the way a surveyor assumes the ground stays put while he measures it. Quantum mechanics, as it matured in the 1920s, threatened both commitments at once. The theory was built around a mathematical object called the wavefunction, evolving in time according to the Schrödinger equation, which we can write as I h bar times the time derivative of the state equals the Hamiltonian acting on the state. In plain language, the quantum state changes smoothly and predictably over time, driven by the system's energy. That much is deterministic. The strangeness enters at measurement. Before you measure, the wave function can describe a particle as being in a superposition, not here or there, but a weighted combination of both. And when you do measure, the Born rule tells you only the probability of each outcome. The probability of finding a given result equals the square of the amplitude associated with it. Randomness enters exactly there, at the act of looking. To Einstein, this was not a description of reality. It was a description of ignorance dressed up as physics. He suspected the theory was incomplete, that beneath the probabilities lay definite facts the theory failed to capture. The way a weather forecast gives you a 60% chance of rain, not because the atmosphere is undecided, but because your knowledge is limited. That suspicion is the seed of what physicists call hidden variable theory, the proposal that particles carry definite properties all along, and quantum probabilities merely reflect our failure to see the hidden details. So, in 1935, with two younger collaborators, Boris Podolsky and Nathan Rosen, Einstein published a paper in the journal Physical Review with a title phrased as a question: Can quantum mechanical description of physical reality be considered complete? It ran barely 4 pages. The New York Times covered it under the headline, "Einstein Attacks Quantum Theory," and the argument it contained would occupy the best minds in physics for the next 50 years. Their reasoning went like this. Imagine two particles that interact and then fly apart, their properties linked by the conservation laws of that interaction. Measure the position of the first, and because of the correlation, you instantly know the position of the second without touching it. Measure instead the momentum of the first, and you instantly know the momentum of the second. Now, quantum mechanics, through Heisenberg's uncertainty principle, forbids any particle from having both a definite position and a definite momentum at the same time. But here, you could predict either one for the second particle with certainty without ever disturbing it. And Einstein, Podolsky, and Rosen argued that if you can predict a quantity with certainty without disturbing the system, then that quantity must correspond to an element of physical reality. It must be there whether you look or not. The conclusion seemed inescapable to them. Either the distant particle secretly had both a definite position and a definite momentum all along, in which case quantum mechanics, which denies this, is incomplete. Or else, the act of measuring the first particle instantly created the reality of the second, across whatever gulf of space separated them. That second option struck Einstein as absurd, a violation of locality so severe he could only call it spooky. He was certain the first option was correct. The theory was unfinished. There were hidden variables waiting to be found. Consider what this argument really asks. Two locksmiths are handed two halves of a single broken key, sealed in envelopes, and sent to opposite ends of a continent. When the first locksmith opens her envelope and sees the left half, she knows instantly the shape of the right half in the other envelope. Nothing traveled. No message was sent. The correlation was set at the moment the key was broken, and the knowledge was waiting to be revealed. This is exactly how Einstein wanted entanglement to work. as pre-existing facts established when the particles parted, carried along like sealed envelopes. Common cause, not spooky influence. What does it mean that this reasonable, almost self-evident picture turns out to be wrong? Keep the sealed envelopes in mind. We will return to them. The word for the connection came not from Einstein, but from Erwin Schrödinger, who read the EPR paper and was galvanized by it. In a paper of his own that same year, he introduced the German term Verschränkung, which we translate as entanglement, and he called it not one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. He also coined a second term, steering, for the unsettling way a measurement on one particle seems to steer the state of its partner. Schrödinger saw more clearly than almost anyone that entanglement was not a peripheral oddity. It was the center of the whole strange edifice. Niels Bohr, the architect of what became known as the Copenhagen interpretation, replied within months in a paper carrying the very same title as EPRs. His answer was subtle and, to many readers, maddeningly opaque. Bohr rejected the EPR criterion of reality itself. He argued that it makes no sense to speak of a particle's position or momentum as a pre-existing element of reality, independent of the entire experimental arrangement used to measure it. The apparatus and the system form an indivisible whole. You do not uncover a pre-existing value. The possibility of defining that value is created by the measurement context. To ask what the distant particle's momentum really was, before and independent of any measurement, was for Bohr a question without physical meaning. The Copenhagen interpretation, in Bohr's hands, did not so much refute EPR as refuse its central assumption. This is the Bohr-Einstein debate, one of the great intellectual confrontations of the 20th century. Two of its deepest thinkers disagreeing not about any calculation, for they agreed on every prediction quantum mechanics made, but about what the mathematics meant. Einstein held that physics must describe a reality in space and time, free from spooky action at a distance. Bohr held that at the quantum level, that very demand was a prejudice inherited from a classical world that does not, at bottom, exist. For nearly 30 years, this looked like a dispute philosophers could argue forever, because there seemed to be no experiment that could tell the two views apart. Both agreed on what the instruments would read. They disagreed only on the story behind the readings. Here, I want to pause on something that still strikes me. For 3 decades, the greatest question in the foundations of physics was considered essentially unanswerable, a matter of taste, of interpretation, of metaphysics beyond the reach of the laboratory. The consensus was that you could not test it. That consensus was wrong, and the person who proved it wrong was not a famous man at the time, but a physicist working in his spare hours on a problem everyone else had filed away as unresolvable. His name was John Stewart Bell, a Northern Irish physicist employed at the CERN Particle Physics Laboratory, whose day job had nothing to do with the foundations of quantum theory. In 1964, in a short paper published in an obscure journal called Physics, he did something that had eluded everyone before him. He took Einstein's own assumptions, local realism, the sealed envelope picture, hidden variables carried along from a common origin, and he asked a precise mathematical question. If Einstein is right, if the correlations between entangled particles are set in advance by hidden variables, and no influence travels faster than light, then how strongly can the measurements on the two particles be correlated across a range of different detector settings? He found that local realism imposes a strict ceiling. There is a limit to how well coordinated the two sides can be. And quantum mechanics, he showed, predicts correlations that exceed that ceiling. This is the content of Bell's theorem, and it stands among the most profound results in the history of science, because it converted a philosophical dispute into an experimental one. Einstein's worldview was no longer a preference. It made a prediction, a numerical bound, and quantum mechanics made a different prediction. Nature would decide between them. His original inequality can be written as the absolute value of the difference between two correlations, E of A minus B minus E of A minus C, being less than or equal to 1 plus E of B minus C, a triangle-like constraint on how correlations measured at three different angles can relate. In plain terms, if the world is locally real, correlations at different measurement angles must obey this bound. Break the bound, and local realism is false. This is what we will return to again and again, so hold on to it. Bell found a number that Einstein's universe cannot exceed. A few years later, in 1969, four physicists, John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, refined Bell's insight into a form built for the laboratory. Their version is called the CHSH inequality, after their initials, and it is the workhorse of every experiment we are about to discuss. It states that a particular sum of four correlation measurements, S, has an absolute value that stays at or below 2 if the world is locally real. Written out, S is the absolute value of E of A minus B plus E of A minus B prime plus E of A prime B minus E of A prime B prime. Here, each E is the correlation between the plus or minus 1 outcomes at the two detectors, and A prime, B prime are the settings the experimenters choose on each side. The number 2 is the classical ceiling, Einstein's ceiling. It is the highest value any theory built on hidden variables and locality can produce. Quantum mechanics, applied to entangled particles at the right angles, predicts a value as high as 2 times the square root of 2, approximately 2.828. Sit with that gap for a moment. 2 versus 2.828. It does not look like much, but it is the entire difference between a universe of sealed envelopes and a universe of spooky action. It is the difference between Einstein's world and Bohr's, reduced to a decimal. Everything now depended on going into a laboratory and measuring which number nature actually produces. The first serious attempt came in 1972, at the University of California, Berkeley, and the nearby Lawrence Berkeley Laboratory, where a young experimentalist named John Clauser, the same Clauser of CHSH, worked with a graduate student, Stuart Friedman. They used calcium atoms, exciting them so they emitted pairs of photons in a cascade, the two photons entangled in their polarization. They sent each photon toward a polarizer and measured how often the two agreed. The result violated Bell's bound by roughly 6 standard deviations, 6 sigma in the language of statistics, meaning the odds of such a result arising by chance, if local realism held, were vanishingly small. Quantum mechanics was winning. Einstein's ceiling had been breached. But, and this word will recur throughout our story, the experiment was not airtight. It had loopholes, gaps in the logic through which a determined defender of local realism could still escape. Understanding these loopholes is essential, because the entire experimental history of the EPR paradox over the next 43 years is the history of closing them, one by one, until there was nowhere left to hide. The first loophole is the locality loophole. In the 1972 experiment, the two detectors sat close together, and the settings were fixed in advance. In principle, a signal travelling at or below the speed of light could have passed from one detector to the other during the measurement, carrying information about which setting was chosen, allowing the particles to coordinate their answers the old-fashioned way. To close this loophole, you must choose the detector settings so quickly and place the detectors so far apart that no such signal could possibly cross between them in time. The choice at one station and the measurement at the other must be separated by a space-like interval, meaning light itself cannot bridge them. The second is the detection loophole, sometimes called the fair sampling loophole. Real detectors miss most of the particles that reach them. If the particles that happen to get detected are not a fair sample of all the particles emitted, if somehow the ones that slip through are precisely the ones that would have restored Einstein's bound, then the violation you measure might be an artifact of your inefficient equipment. To close this loophole, you need detectors efficient enough to catch a large enough fraction of the pairs. The third, and most philosophically loaded, is the freedom of choice loophole. The whole logic of Bell's theorem assumes that the experimenter's choice of detector setting is genuinely free, independent of the hidden variables carried by the particles. But what if it is not? What if some common factor in the past influenced both the particles' hidden properties and the settings the experimenter would later choose? Then the correlation could be faked without any spooky action at all. This is the loophole that will carry us eventually to quasars at the edge of the observable universe. Keep it in mind. We will need it. The man who first attacked the locality loophole head-on was the French physicist Alain Aspect, working at the Institut d'Optique in Orsay, near Paris. In 1982, Aspect and his colleagues Jean Dalibard and Gérard Roget built an experiment with a crucial new feature: switches that redirected each photon toward one of two differently oriented polarizers. And these switches flipped extraordinarily fast, driven by acousto-optic devices oscillating near 50 MHz, changing the photon's path roughly every 10 nanoseconds. That was faster than the time it would take light to travel between the two stations. The setting on each side was chosen, in effect, only after the photons were already in flight, too late for any light-speed signal to coordinate them. This dynamically addressed the locality loophole for the first time. The normalized result came in at around 5 standard deviations of violation. A companion experiment from the same group, using a static 2-channel setup, measured the CH-SH parameter S at 2.697, plus or minus 0.015, comfortably above the classical ceiling of 2, and strikingly close to the quantum prediction of about 2.70. Picture the Orsay laboratory. A source of calcium atoms glowing at the center, photons streaming outward along 2 arms of the apparatus, and at the end of each arm, a switch, flickering millions of times a second, hurling each photon left or right toward polarizers set at angles no signal could anticipate. The correlations held. They matched quantum mechanics, not Einstein. In 1998, Anton Zeilinger and his group in Innsbruck, Austria, tightened the locality loophole further, using fast random number generators to set the polarizer angles, and separating the detectors by hundreds of meters, ensuring a clean, space-like separation between the 2 measurement events. The violations stood, sharper than ever. Piece by piece, the escape routes for local realism were narrowing. And yet, notice what still remained. Through all of this, the detection loophole stayed open. The photon detectors of the era caught only a small fraction of the pairs. A committed skeptic could still argue that the detected sample was rigged by nature to mimic quantum mechanics. And no single experiment had yet closed the locality loophole and the detection loophole at the same time. To silence the objection completely, you needed one experiment that shut both doors at once. That experiment would not arrive for another 17 years. What does it mean that a result can be confirmed again and again over decades and still leave a crack through which doubt can crawl? This is not weakness in the science, it is the opposite. It is the refusal to declare victory until every alternative has been strangled. Before we cross into the era of loophole-free tests, there is one more thread we must lay down, because it will matter enormously later. It is the question of why, if entanglement links particles instantly across space, you cannot use it to send a message faster than light. Einstein feared spooky action would let information outrun light and shatter relativity. It does not. And the reason it does not is protected by 2 of the most elegant results in all of quantum theory. The first is the no signaling principle. When you measure your half of an entangled pair, the outcome you get is random, genuinely, irreducibly random. You see a stream of coin flips, noise, and nothing more. The distant partner, measuring her half, also sees pure noise. The correlation between your results only becomes visible when the 2 of you bring your records together and compare them, line by line. And that comparison requires an ordinary channel, a phone call, an email, a signal that crawls along at or below the speed of light. Mathematically, the statistics you see on your side alone, described by what physicists call the reduced density matrix, are completely unchanged, no matter what setting your distant partner chooses. Her choices leave no fingerprint on your data. There is nothing in your stream of results that could tell you what she did. The message is not slow. There is no message. Think about two accountants in separate offices, each handed a long list of random numbers. Unknown to them, the lists were generated together, so that when finally laid side by side, every entry matches in a subtle, statistically loaded way. But until they meet and compare, each sees only noise on their own desk. Neither can read anything in their own column. The pattern lives only in the relationship between the two columns. And to see the relationship, you must physically bring the columns together. That is entanglement's strict rule. The correlation is real, but it is locked until the two halves are reunited through an ordinary sublight channel. The second result is deeper still, and it is the true mathematical shield. It is called the no-cloning theorem. In 1982, the same year as Aspect's experiment, a physicist named Nick Herbert circulated a proposal he called FLASH, a scheme to send superluminal signals using entanglement. The trick was to make many copies of the quantum state of one particle, so that by examining the copies, you could read off what your distant partner had done. If you could clone an unknown quantum state, you could beat no signaling and send a message faster than light. Herbert's proposal was wrong, but showing exactly why it was wrong led William Wouters and Wojciech Zurek, and independently Dennis Deeks, to prove a fundamental impossibility. The no-cloning theorem states that an arbitrary unknown quantum state cannot be perfectly copied. The proof is beautiful in its brevity. Suppose you had a machine that could copy any state, that took a state psi and a blank, and produced two copies of psi, and likewise took a state phi and produced two copies of phi. Quantum evolution must be linear and preserve inner products. Take the inner product of the two input situations and the two output situations, and you are forced into the equation that the inner product of psi and phi must equal its own square. A number equal to its own square can only be 0 or 1. In plain language, a perfect copier would demand that the overlap between two states equals its own square, which is impossible unless the states are identical or perfectly perpendicular. So, copying an arbitrary unknown state is forbidden by the basic structure of quantum mechanics. Here is the connection that I find genuinely beautiful, the kind of thing I had to sit with for a while when I first understood it. The very same theorem that forbids a quantum photocopier is what enforces relativistic causality. No cloning is not a separate rule bolted on to save relativity. It falls straight out of the mathematics of quantum states. And it happens to be exactly what stands between entanglement and a faster-than-light telegraph. The universe connects everything instantly. But the no-cloning theorem quietly guarantees that signals cannot ride that connection. Keep this shield in mind. When we reach the resolution, it will be the hinge on which the whole question turns. Now the story enters its modern, decisive phase, the era when the loopholes were finally closed together, and the 50-year argument between Einstein and Bohr reached, on the experimental level, a verdict. The year was 2015, and it produced not one, but 3 landmark experiments in rapid succession. The first came from Delft in the Netherlands, from a team led by Ronald Hansen at the institute now called Q-Tech. Their approach was ingenious. Instead of photons, which are easily lost, they used electron spins trapped in nitrogen vacancy centers, tiny defects in diamond crystals, held in 2 laboratories 1,300 meters apart, about 0.8 of a mile, on opposite sides of the Delft campus. The trick was a technique called entanglement swapping. Each electron spin was first entangled with a photon. The 2 photons were sent to a station midway between the labs and made to interfere. And that interference, when it succeeded, left the 2 distant electron spins entangled with each other, without the electrons ever having met. Because the electron spins could be read out with near-perfect efficiency, and because the labs were far enough apart to enforce a space-like separation between the setting choices and the measurements, this single experiment closed the detection loophole and the locality loophole at the same time. It was the first genuinely loophole-free Bell test. The measured CHSH value was 2.42. A combined analysis gave 2.38, plus or minus 0.14, with a probability of only about 4% that local realism could produce such a result by chance across the trials they ran. 245 trials gathered over 220 hours of painstaking data collection. Consider the patience that number represents. 220 hours, more than 9 full days, of a delicate quantum apparatus running to collect just 245 valid events, each one a photon interference success, linking 2 flecks of diamond a kilometer apart. This is what closing a loophole actually costs. Later that same year, 2 photon experiments pushed the statistics far higher. At the National Institute of Standards and Technology in Boulder, Colorado, a team led by Lyndon Sham and Se-Woo Nam ran a test with detectors 185 meters apart, about 607 feet, using a new generation of superconducting nanowire single-photon detectors, with efficiencies above 90%, well past the threshold of roughly 72.5% that a careful analysis showed was required to close the detection loophole. Their paper carried the confident title, "Strong Loophole-Free Test of Local Realism." Almost simultaneously, in Vienna, a group including Marissa Justina and Anton Zeilinger ran a similar photon test in the sub-basement of the Hofburg Palace, detectors 60 meters apart, each registering at least 75% of the photons that reached it. Their paper was titled Significant Loophole-Free Test. 3 experiments, 3 technologies, diamond spins and 2 flavors of high-efficiency photonics, and all 3 agreed. Local realism was dead as a complete description of nature. Einstein's ceiling had been broken with every escape route sealed. But recall the third loophole, the subtle one, freedom of choice. Even in the loophole-free tests of 2015, the detector settings were chosen by random number generators located in the laboratory, moments before each measurement. A superdeterminist, a defender of the idea that the experimenter's choices are secretly correlated with the particle's hidden variables, could still argue that some influence in the recent past had rigged both the settings and the two particles together. To attack this, you would need to make your setting choices depend on something so remote, so ancient, so causally disconnected from the experiment that no conspiracy could plausibly have coordinated it. And this is where the story lifts its eyes from the laboratory bench to the sky. In 2016, before the cosmic tests, came an experiment of a completely different character, the Big Bell test. Rather than using machines to generate the random settings, the organizers recruited about 100,000 human volunteers around the world who, through an online video game, generated more than 97 million binary choices. 97,347,490 of them streamed in real time to 12 laboratories on 5 continents, running 13 different experiments over a single 12-hour period, at rates exceeding 1,000 bits per second. The idea was to use human free will, however one wishes to define it, as the source of the setting choices, replacing the random number generator with the unpredictable decisions of 100,000 people. The Bell violations held across the board. If human choices are free in any meaningful sense, the settings were not secretly correlated with the particles. Then came the cosmic Bell tests, and this is where I find the whole enterprise reaches a kind of grandeur. The theoretical drive came from a team at MIT led by David Kaiser and the cosmologist Alan Guth, the same Guth known for the theory of cosmic inflation. Their idea was to determine the detector settings not from a laboratory random number generator and not from human volunteers, but from the light of distant astronomical objects, arriving at the telescope after traveling across space for centuries or eons. The color of an incoming photon from a distant star would decide in real time which setting the detector used. Because that light was emitted long ago and far away, any hidden conspiracy that hoped to coordinate the settings with the particle's properties would have had to have been arranged at the moment that light was emitted, pushing the required conspiracy deep into the cosmic past. The first cosmic Bell test in 2017 used light from 2 Milky Way stars to set the detectors, with the 2 stations about 2 kilometers apart in Vienna. The violations came in at 7.31 standard deviations in one run and a staggering 11.93 standard deviations in another, the probability of a chance result in that second run smaller than 4 in 100 billion. The consolidated CHSH value, as reported in Kaiser's later review, was around 2.502. The following year, 2018, the team went further, much further. In an experiment led by Johannes Hansteiner and reported by Dominik Rauch and colleagues, they used the light of quasars, the blazing cores of distant galaxies, to set their detectors. The two quasars sat at very different distances, one at a redshift of 0.964, its light emitted roughly 7.78 billion years ago, the other at a redshift of 3.911. Its light emitted roughly 12.21 billion years ago, when the universe, at 13.8 billion years old today, was less than 2 billion years into its existence. The telescopes, the 3.58-meter Telescopio Nazionale Galileo and the 4.2-meter William Herschel telescope, sat on the ridge of Roque de los Muchachos on the island of La Palma. Real-time measurement of each quasar photon's color set the corresponding detector. The Bell violation came in at 9.3 standard deviations, from more than 30,000 photon pairs. This arrangement excluded any local realist conspiracy from 96% of the space-time volume of the experiment's past light cone. Let Alan Guth say what that means, in his own words. If some conspiracy is happening to simulate quantum mechanics by a mechanism that is actually classical, that mechanism would have had to begin its operations somehow knowing exactly when, where, and how this experiment was going to be done, at least 7.8 billion years ago. That seems incredibly implausible. So we have very strong evidence that quantum mechanics is the right explanation. And David Kaiser added the perspective that stays with me most. The Earth is about 4.5 billion years old. So any alternative mechanism, different from quantum mechanics, that might have produced our results by exploiting this loophole, would have had to be in place long before even there was a planet Earth, let alone an MIT. So we've pushed any alternative explanations back to very early in cosmic history. Think about what these people actually did. To close a logical loophole in an experiment about two particles on a tabletop, they reached out to the light of a galaxy that blazed 12 billion years ago and let that ancient light decide which way to turn a switch. There is a picture worth holding in your mind. A photon that left a quasar when the universe was young, that crossed the growing gulf of an expanding cosmos for 12 billion years, that fell at last through a telescope on a volcanic ridge and, in its final microsecond of existence, chose the angle of a polarizer. I have never encountered a more vivid demonstration of how far physicists will go to leave no place for doubt to hide. The distances involved in these experiments span an extraordinary range, and they're worth laying side by side. The ETH Zurich experiment, which we will come to, used a link of just 30 meters. Vienna's photons were separated by 60 meters, NIST's by 185. Delft's diamonds sat 1,300 meters apart, and the Mitsier's satellite distributed entanglement between ground stations 1,200 kilometers apart, roughly 746 miles. That Mitzius result, published in 2017 by a team led by Jian-Wei Pan, distributed entangled photon pairs from a satellite orbiting about 500 kilometers up to two mountaintop observatories and still measured a Bell violation of 2.37 plus or minus 0.09 under strict conditions enforcing space-like separation. The satellite link was between 12 and 17 orders of magnitude more efficient at delivering photons over that distance than the best optical fiber would have been. A difference so vast, it is the reason the experiment was possible at all. And in 2023, a team at ETH Zurich, led by Simon Storz and Andreas Wollraff, performed a loophole-free Bell test using superconducting qubits, not photons, not diamond spins, but circuits of superconducting metal, connected by a 30-meter cryogenic link cooled to nearly absolute zero, around minus 273 degrees Celsius. 30 meters is close to the minimum distance at which a loophole-free test is even possible, because light takes only about 110 nanoseconds to cross it, and every setting choice and measurement had to be squeezed inside that fleeting window. Over more than 1 million trials, they measured a CHSH value of 2.0747 plus or minus 0.0033, modest in size but overwhelming in certainty, with a probability of a chance fluctuation smaller than 10 to the minus 108, more than 22 standard deviations. That is not a result that leaves room for argument. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger, in the words of the citation, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. 57 years after Bell wrote his theorem, 90 after Einstein wrote his paper, the argument had a verdict and the Nobel Committee recognized it. What does it mean that a debate everyone once thought was pure philosophy, untestable, a matter of taste, ended in a Nobel Prize for the people who tested it? It means that the boundary between physics and metaphysics is not fixed. It can move. Bell moved it. So we have, established beyond reasonable doubt, three facts. Non-local correlations are real. They cannot be explained by any theory of local hidden variables, of sealed envelopes carried along from a common origin. And yet, the no-signaling principle has never once been violated. You cannot send a message through the connection. These three facts are the settled bedrock. Everything I have described so far is, in the language of physics, not controversial. It is confirmed, checked, cross-checked, and honored with the field's highest prize. But confirming that the correlations are real does not tell us what they are. It does not tell us what is actually happening when you measure one particle and its distant partner responds. Bell's theorem tells us what nature is not. It is not locally real. It does not tell us what nature is. And here, beneath the settled experiments, lies a landscape of competing scientific pictures, each of which reproduces every experimental result perfectly, each of which tells a radically different story about what lies underneath. This is where the deeper exploration begins, because to understand the EPR paradox fully, you have to understand not just that Einstein was wrong about local realism, but what the possible replacements for his worldview actually are. Bell's theorem, stated carefully, says this: no theory that is both local and based on pre-existing definite values, and that respects the experimenter's freedom to choose settings, can reproduce the correlations quantum mechanics predicts and experiments confirm. Read that again, because the structure of it matters. It is a theorem with several assumptions, and to escape its conclusion, you must give up at least one of them: locality. Definite pre-existing values, which physicists call realism, or sometimes definite outcomes. Or freedom of choice. Every interpretation of quantum mechanics that takes the experiment seriously is, at bottom, a decision about which of these assumptions to sacrifice. And that choice is not forced by the data. The data are silent on it. That silence is the heart of what remains open. Let me lay out the contenders fairly as they see themselves, because in the resolution we will weigh them, and to weigh them fairly we must first understand them on their own terms. The orthodox position is the Copenhagen interpretation, descended from Bohr. In its modern form, it treats the quantum state as a complete description of what can be said about a system, declines to assign definite values before measurement, and regards the measurement outcome as a genuinely new fact brought into being by the act of measurement in a definite experimental context. Copenhagen gives up realism in Einstein's strong sense. The particle simply does not have a definite spin along an unmeasured axis. What it keeps is a kind of locality, because it denies there was ever a definite value at the distant particle to be spookily changed. There was only a correlation waiting to be revealed in the joint statistics. Copenhagen is minimal. It matches all the data, and its critics say it is vague about exactly where measurement begins and the smooth quantum evolution ends, the so-called measurement problem, the unresolved question of how and when the fuzzy superposition of the wave function becomes a single sharp outcome. The second contender is the one Einstein might have found most congenial, though he never embraced it: Bohmian mechanics, also called the de Broglie-Bohm theory or pilot wave theory, first sketched by Louis de Broglie in 1927 and fully developed by David Bohm in 1952. Bohmian mechanics keeps realism in the fullest sense. Every particle always has a definite position at every moment, whether observed or not. There is no collapse, no fuzziness in the underlying reality. Instead, particles are guided by the wave function, which acts as a pilot wave, steering them along definite trajectories. It reproduces every prediction of standard quantum mechanics exactly. It is empirically indistinguishable. It restores the definite, deterministic world Einstein longed for. But it pays a steep price, and the price is precisely the thing Einstein could not stomach. Bohmian mechanics is explicitly, unavoidably, non-local. In the pilot wave picture, the guiding wave for two entangled particles depends instantaneously on the positions of both, no matter how far apart they are. Moving one particle here instantly changes the guiding influence on the particle there. And this instantaneous connection requires something troubling for relativity, a preferred foliation of spacetime, a privileged slicing of the four-dimensional world into surfaces of now, along which the non-local influence acts simultaneously. As one careful statement in the literature puts it, Bohmian mechanics is incompatible with special relativity. It is not Lorentz invariant. It buys realism at the cost of a hidden preferred frame. To see why a preferred frame is such a heavy cost, recall what relativity tells us through the Lorentz transformation, the equations that describe how space and time measurements change between observers moving relative to one another, with the factor gamma, 1 over the square root of 1 minus velocity squared over the speed of light squared, stretching time and contracting space as you approach light speed. The deep lesson of these equations is that simultaneity is relative. Two events that are simultaneous for one observer are not simultaneous for another moving differently. There is no universal now. But an instantaneous non-local influence, the kind Bohmian mechanics requires, needs exactly such a universal now to define what instantaneous even means. That is the tension. Relativity says there is no preferred slicing of time. Bohmian mechanics quietly requires one. The theory works, and it is Lorentz invariant in its observable predictions, but underneath, at the level of the real, it needs a frame that relativity says should not exist. The third contender takes a breathtakingly different route. It is the many worlds interpretation proposed by Hugh Everett in 1957. Many worlds keeps the smooth Schrödinger evolution and throws away collapse entirely. There is no single outcome to a measurement. When you measure an entangled particle and find spin up, the version of you who found spin down also exists in a branch of the universal wave function that has decohered from yours. Every outcome happens. Reality branches. The startling payoff is that many worlds can be described as local in a certain sense, because nothing collapses, nothing needs to be instantaneously changed at a distance. The correlation is established only when the two branches, the two records, are finally brought together and compared. And at that point, the local interaction of comparison sorts out which branches match which. What many worlds surrenders is not locality, but the assumption of definite single outcomes. The idea that a measurement has one result. It pays instead with the reality of the entire, endlessly branching universal wave function, and with two hard technical problems. The preferred basis problem of why the world branches along the particular divisions we experience, and the probability problem of how to make sense of the Born rule's probabilities in a picture where every outcome definitely occurs. The fourth contender bites a different bullet: objective collapse theories, the best known being the GRW model of Girardi, Rimini and Weber from 1986. Here, collapse is not a vague addendum, but a real physical process built into the dynamics. The wavefunction spontaneously localizes at random, extraordinarily rarely for a single particle, but almost instantly for the trillions of particles in a measuring device, so that macroscopic superpositions collapse essentially at once. GRW solves the measurement problem by making collapse objective and law-like. Its cost is new fundamental constants of nature, chosen to fit the rate and scale of spontaneous collapse, along with technical difficulties over energy conservation and a dynamics that is time asymmetric by hand. Crucially, GRW is testable and experimentally constrained. Unlike the others, it predicts small deviations from standard quantum mechanics in the right regime, which means that one day, in the laboratory, it could be confirmed or ruled out. Hold on to that. It will matter when we ask what could ever break the tie. The fifth contender relocates the entire puzzle. It is cubism, short for quantum Bayesianism, developed by Christopher Fuchs, Rudiger Schack, and N. David Mermin. Cubism says the quantum state is not a fact about the external world at all. It is an agent's degrees of belief, a personal Bayesian bookkeeping of expectations about the outcomes of the agent's own future experiences. Collapse, in this view, is nothing mysterious. It is just what happens to your beliefs when you learn a new fact, the ordinary Bayesian update. And on this reading, the non-locality paradox simply dissolves. When you measure your particle and instantly know the distant particle's state, nothing physical has changed over there. Only your personal expectations have updated. Locality is preserved because there was never a physical non-local influence to begin with, only the revision of one agent's knowledge. Cubism's cost is that it appears to retreat from realism about the external world altogether. Critics charge it with anti-realism or even solipsism. Its proponents answer with what they call participatory realism, and Fuchs puts the spirit of it this way: reality is more than any third-person perspective can capture. What cubism surrenders is the assumption that the quantum state describes the world, rather than an agent's engagement with it. There are further contenders, more radical still. Retrocausal or time-symmetric interpretations, developed by Hugh Price, Ken Wharton and others, propose that influences can travel backward in time along the light cone, so that the detector setting you choose now can influence the particle's properties in the past, at the moment of emission. This aims to restore full Lorentz invariance and eliminate spatial non-locality entirely, a very attractive prize. What it surrenders is the assumption that causes precede effects, forward-only causation. Its cost is that no complete empirical model yet exists, and it faces objections about fine-tuning. Price has articulated a striking thesis, that if you insist on realism, time symmetry, and a certain discreteness, retrocausality follows almost inevitably. And at the far edge lies superdeterminism, advocated by Gerhard Hooft and Sabine Hossenfelder, which attacks the freedom of choice assumption directly. If the settings the experimenter chooses were themselves correlated from the beginning with the hidden variables of the particles, if there is no genuine independence between choice and system, then local realism could survive after all. Superdeterminism is the loophole the cosmic Bell tests were designed to strangle. And while it cannot be strictly disproven, the cost it demands is severe. A universe fine-tuned from its earliest moments to coordinate every future experimental choice with the properties of every particle to be measured. A cosmic conspiracy that, as we saw, would have to have been arranged 12 billion years ago. It also threatens to undermine the very possibility of doing experiments, since it denies that we can freely vary what we test. Now, before we weigh these against each other, there is one more question that cuts underneath all of them. And it is perhaps the sharpest question in the whole field. Is the quantum state, the wave function itself, a real physical thing out there in the world? Or is it merely a representation of our knowledge, our information, about the world? Physicists have names for the two positions. If the wave function is real, physically existing, they call it psi-ontic, from the Greek for being. If it is merely knowledge or information, they call it psi-epistemic, from the Greek for knowledge. Einstein leaned epistemic. He wanted the wave function to be like a probability distribution, a statement of incomplete information about an underlying reality. Cubism is the modern heir of that impulse. Copenhagen and many worlds and Bohmian mechanics, in their different ways, treat the wave function as ontic, as part of reality. For a long time, this too seemed like an untestable matter of taste. Then, in 2012, three physicists, Matthew Pusey, Jonathan Barrett, and Terry Rudolph, proved a theorem, now called the PBR theorem, that constrains it sharply. They showed that under an assumption they called preparation independence, the reasonable-sounding idea that systems prepared separately, independently, have independent underlying real states, the quantum state cannot be purely epistemic. It must be ontic. Two distinct quantum states cannot correspond to the same underlying reality if preparations are independent. In plain terms, if you prepare two systems separately and their real states are independent, then different wave functions must describe genuinely different realities, not just different states of knowledge about the same reality. The PBR theorem is often summarized as showing that the wave function is real. And I remember the first time I followed the argument, thinking that it felt almost too strong, that something this fundamental should not fall out of an assumption as modest as separately prepared things are separate. That reaction, it turns out, is exactly where the debate still lives. Notice what this deeper layer requires us to accept. Every one of these interpretations reproduces every experimental result. Not approximately, exactly. For every measurement humans have ever made or can currently make, Copenhagen, Bohmian mechanics, many worlds, GRW in its allowed range, cubism and the rest give the identical prediction. The mathematics works. But what does it mean? What does it mean that we have a theory of unprecedented precision, confirmed to more than 22 standard deviations, and we cannot agree on what it says about the world? The equation predicts. The equation does not interpret itself. There is one more thread to lay down before we turn to weigh all of this, the strangest and most beautiful of them all, and the one that points toward the frontier. It begins with a theorem from 1961, proved by Helmut Rey and Siegfried Schlieder in the framework of quantum field theory. The Rey-Schlieder theorem concerns the vacuum, empty space, the state of lowest energy, apparently nothing at all. And it shows something almost paradoxical, that the vacuum is a cyclic vector, meaning that by acting with local operations confined to any tiny region of space, you can approximate any state at all, anywhere in the universe. Written loosely, operators acting locally on the vacuum state can generate a dense set of all possible states. The physical meaning is staggering. The vacuum is not empty in the sense of being unstructured. It is threaded everywhere with correlation. Empty space is deeply, intricately entangled with itself across every boundary. In 2003, Benny Resnick took this from abstract theorem to concrete proposal in a paper titled Entanglement from the Vacuum. He showed that two detectors, idealized two-level systems that physicists call Unruh DeWitt detectors, placed in separate regions of empty space, each coupling only locally to the quantum field, could become entangled with each other, even if they are so far apart that no light signal could pass between them during the interaction. They do not exchange anything. They each simply interact locally with the pre-existing entanglement woven into the vacuum, and in doing so, they harvest some of it, drawing entanglement out of the empty space between them. This process, called entanglement harvesting, remains to this day a theoretical prediction. No laboratory has yet demonstrated it, but it is being actively developed, extended to curved spacetime, to the vicinity of black holes, even to the entanglement latent in the gravitational vacuum. The amount harvested can be quantified by a measure called negativity, computed from the partial transpose of the joint state. When it is positive, entanglement is present. What does it mean that empty space itself carries the same ghostly correlations we found between our particles? That the nothing between things is quietly full of the very connection we have been chasing? Hold this thread. It leads somewhere remarkable. Because in 2013, two theorists, Juan Maldacena and Leonard Susskind, proposed a conjecture that, if true, would tell us what entanglement fundamentally is. It is called ER equals EPR, and it is one of the boldest ideas in modern physics. The ER stands for Einstein-Rosen bridge, a wormhole, a tunnel through space-time connecting two distant regions, first described by Einstein and Rosen in that same fertile year of 1935, the same Rosen of the EPR paper. The EPR stands for the entanglement of the EPR paradox. Maldacena and Susskind conjectured that these two things, a wormhole and an entangled pair, are the same thing, seen two ways. Two entangled black holes, in their picture, are connected by a non-traversable Einstein-Rosen bridge. And, more generally, entanglement between any two systems might be, at the deepest level, a microscopic wormhole connecting them. In their words, the Einstein-Rosen bridge between two black holes is created by EPR-like correlations between the microstates of the two black holes. If this is right, the implication reorders everything. Entanglement would not be a connection across space. It would be the very thing that stitches space together in the first place. Susskind put it vividly. Entanglement provides the spatial connectivity that sews space together. Maldacena said that the solid and reliable structure of space-time is due to the ghostly features of entanglement. On this view, the reason two points in space are near each other, connected, part of the same smooth continuum, is that the quantum degrees of freedom at those points are entangled. Cut the entanglement, and space itself would come apart. This idea grew from a body of work in holography, especially the Ryu-Takayanagi formula of 2006, which relates the entanglement entropy of a region to geometry with startling directness. The entanglement entropy of a boundary region equals the area of a minimal surface in the bulk divided by 4 times Newton's gravitational constant. Entropy, a measure of entanglement, equals area. Entanglement and geometry on opposite sides of an equal sign. That is not a metaphor. It is an equation. Sit with the sweep of that for a moment. We began with Einstein trying to defend the ordinary, sensible idea that things are only connected when something crosses the space between them. And we have arrived at a serious scientific conjecture that space itself, the very medium of separation, is woven out of the connection Einstein was trying to deny. This is the part of the story I find hardest to put down. The thing he called spooky may be the thread from which the stage is made. I said early on that we would return to the sealed envelopes, to Bell's number, to the no-cloning shield, to the question of what the quantum state really is. Now we do. For the length of this exploration, I have laid out what the evidence shows and what the competing pictures claim, without judging between them. Now we weigh them carefully, on the evidence, on the science, and only on the science. Start with what is genuinely settled, because it is essential not to let the open questions blur the closed ones. Einstein's sealed envelope picture, local hidden variables, definite properties carried along from a common origin with no spooky connection, is dead. Not doubtful, dead. The loophole-free experiments of 2015 closed the locality and detection loopholes together. The cosmic Bell tests of 2017 and 2018 pushed the freedom of choice loophole back to within a fraction of the age of the universe, excluding any local realist conspiracy from 96% of the past light cone. The ETH Zurich experiment of 2023 confirmed the violation to more than 22 standard deviations, with odds against chance smaller than 10 to the minus 108, a number with no meaningful comparison in ordinary experience. Across photons, electron spins in diamond, and superconducting circuits, across distances from 30 meters to 1,200 kilometers, the answer is always the same. The correlations exceed Bell's classical bound of 2, climbing toward the quantum ceiling of 2.828. The universe is not locally real. Einstein's specific proposal that quantum mechanics is incomplete because hidden variables and locality together explain everything is refuted. That is the resolution of the question he actually posed, and the evidence for it is as strong as evidence gets in physics. Now, the second settled fact, and it is the answer to our title. Despite all this, no signaling has never been violated. Not in a single experiment across 50 years. The correlations are real and instantaneous in the sense that measuring one particle immediately fixes the joint statistics. But the local statistics on either side alone are pure noise, unaffected by anything the distant experimenter does. You cannot encode a message. And the deep reason, the mathematical shield, is the no-cloning theorem, the impossibility, provable in 3 lines, of copying an unknown quantum state. Nick Herbert's 1982 flash scheme to signal faster than light failed for exactly this reason. And in failing, it revealed that the structure preventing a quantum photocopier is the same structure preventing a faster-than-light telegraph. So the title is not a paradox to be dissolved. It is a precise statement of what the evidence shows. The universe connects everything instantly, in the sense of genuine non-local correlation. But signals cannot cross that connection, because to read the correlation, you must physically bring the 2 records together through an ordinary sub-light channel, and because the no-cloning theorem forbids the one trick that could evade this. Both halves of the sentence are true, and there is no contradiction between them. That is the answer. The third relatively settled point is more subtle. The PBR theorem gives real weight to the view that the quantum state is ontic, physically real, rather than merely a record of our knowledge, provided you accept that independently prepared systems have independent, real states. Under that assumption, the wavefunction is part of reality. But notice the qualifier, because it is where the resolution starts to open rather than close. PBR does not end the debate, it sharpens it. Retrocausal and superdeterministic models can escape PBR precisely by denying the assumption it rests on, by allowing the underlying state to depend on things PBR assumes it cannot. So, PBR narrows the field without emptying it. And that brings us to the genuine open edge, the part where honesty requires me to stop resolving and start naming what the evidence does not settle. Here is the crucial point, and it is easy to miss beneath all the triumphant experiments. Every interpretation I described, Copenhagen, Bohmian mechanics, many worlds, GRW, within its allowed range, cubism, retrocausality, reproduces every experimental result we have. Every one. The data do not choose among them. They cannot, because the interpretations were built to agree with the data. What separates them is not evidence, but cost, which cherished assumption each one is willing to surrender. Weigh them then not by asking which fits the data, since they all do, but by asking what each must give up. Bohmian mechanics keeps a fully definite deterministic reality. Einstein's dream of definite values. But it surrenders locality outright and needs a preferred foliation of spacetime in quiet tension with relativity. Many worlds keeps locality and the smooth, collapse-free evolution of the wavefunction, but it surrenders the idea that measurements have single, definite outcomes. And it owes us a convincing account of where its probabilities come from. Copenhagen keeps things minimal and matches everything, but it surrenders a clear account of where measurement begins, leaving the measurement problem unresolved. Cubism dissolves the non-locality puzzle entirely and keeps locality, but it surrenders the claim that the quantum state describes the external world at all. GRW keeps a single definite reality and solves the measurement problem with law-like collapse, but it surrenders exact agreement with standard quantum mechanics. And that is its great virtue, because it means GRW is testable and could one day be confirmed or killed in the laboratory. Retrocausality could restore full relativistic locality, a genuine prize, but it surrenders forward-only causation and has no complete model yet. Superdeterminism could save local realism, but only by surrendering the freedom to choose what we measure, a price most physicists judge too high, and one the cosmic Bell tests have pushed to the brink of absurdity by requiring the conspiracy to predate the Earth. What would it take to decide among them? Not more Bell tests. Those settle that the correlations are non-local, which every contender already accepts. Deciding among the interpretations would require reaching regimes we cannot yet touch. A confirmed detection of spontaneous collapse would vindicate GRW and eliminate the collapse-free contenders. A laboratory demonstration of entanglement harvesting from the vacuum would sharpen our picture of how deep the field-level entanglement runs. And a genuine signature of quantum gravity, evidence bearing on whether ER equals EPR is literally true, whether entanglement really is the thread from which spacetime is sewn, would reach beneath all of them. These are not idle hopes. They are active research frontiers. But today, the honest statement is this: the physics of the correlations is settled, and the meaning of the correlations is not. We know with overwhelming precision what nature does. We do not yet know, and cannot yet decide by experiment, which story about what nature is happens to be the true one. Before I continue, consider what this means and take a moment with it. We have a theory more precisely confirmed than almost any in the history of science. It never fails. And beneath it sit at least 7 coherent, self-consistent pictures of reality, mutually contradictory, all equally faithful to every measurement. This is not a failure of physics. It is physics arriving with great rigor at the exact boundary of what measurement can currently decide, and having the discipline to say so. And there is a further edge, fainter and deeper, where even this careful map runs out. If ER equals EPR points somewhere true, if entanglement really is what stitches space together, then the connection we have been chasing is not something that happens within space. It is prior to space. It is closer to the reason there is a connected space at all. And that pushes us toward a question the science as it stands cannot answer. Why the world is built this way rather than some other way. Why reality is threaded at its foundation with a connection that binds everything yet carries no message. Here, the equations do not break down so much as fall silent. They describe with breathtaking accuracy how the connection behaves. They do not tell us why there is such a connection to behave at all. That question lies beyond what the measurement can reach, and it is honest to leave it there, open, unclosed, neither answered nor dismissed. Let me bring this exploration to a close. We began with a conversation over tea in 1935, and a 4-page paper in which Albert Einstein, with Boris Podolsky and Nathan Rosen, tried to prove that quantum mechanics was incomplete. His argument rested on 2 commitments that seemed beyond question. Realism, that things have definite properties whether or not we look, and locality, that nothing here can instantly touch something there. From those, through the principle he defended and the spooky action at a distance he could not accept, he concluded there must be hidden variables, sealed like halves of a broken key in separate envelopes. We watched Niels Bohr answer him in the long Bohr-Einstein debate by denying that the distant particle had any definite property to begin with. We watched Erwin Schrödinger name the connection entanglement and call it the defining trait of quantum theory. And we watched John Stewart Bell, working quietly at CERN, turn the whole dispute into a number, the classical ceiling of 2 in the CH-SH inequality that Einstein's universe cannot exceed. Then we followed the experiments, from Friedman and Clauser in 1972, through Aspect at Orsay in 1982, to the 3 loophole-free tests of 2015, the 100,000 human choosers of the Big Bell test, the starlight-driven cosmic test of 2017, the quasar-driven test of 2018 that reached back 12 billion years, the Michius satellite linking stations 1,200 kilometers apart, and the ETH Zurich circuits confirming the violation past 22 standard deviations. We saw the 2022 Nobel Prize crown the 50-year verdict. And we saw why, through all of it, the no signaling principle held, shielded by the no cloning theorem, the same three-line impossibility that blocks a quantum photocopier and, in doing so, guards the speed of light. Here is where the evidence leaves us. Einstein's specific claim was wrong. The universe is not locally real, and no theory of sealed envelopes can reproduce what we measure. That is as settled as physics gets. Yet, the deeper thing he was reaching for, that this connection should not let us signal, should not shatter relativity, turned out to be true. And true for a reason more elegant than he could have known. The correlations are real and instantaneous. The messages are impossible, both at once, without contradiction. And beneath that settled physics lies a menu of interpretations: Copenhagen, Bohmian mechanics, many worlds, objective collapse, cubism, retrocausality, that the data cannot yet separate, distinguished not by any disagreement with experiment, but only by which assumption each is willing to surrender. What separates them is cost, not evidence. That is the honest state of the question. We know what nature does to extraordinary precision. Which story about what nature is remains genuinely open. And only a new regime, spontaneous collapse, vacuum harvesting, or a signature of quantum gravity, could decide it. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. And if the idea that entanglement might not travel through space, but instead build it, that the connection could be the very thread from which spacetime is sewn, is the thought that lingers with you, there is a related exploration waiting on the end screen and in the description, following that question about the fabric of space more deeply than we could here. It is worth your time if this held it. Einstein set out to show that the world could not permit spooky action at a distance. In failing, he uncovered a connection stranger than his objection, one that binds every entangled thing together in an instant, and yet, by a law woven into the mathematics itself, refuses to carry a single word across the gulf it spans. The universe connects everything instantly. Signals cannot follow. Sit with that tonight. A cosmos threaded through with a link that is real, immediate, and mute, carrying no message, and perhaps, if the deepest conjectures hold, holding space itself together. There is a further number in this story that we have not yet examined closely, and it deepens the mystery rather than resolving it. Recall the ceilings, the classical bound of 2 and the quantum bound of 2 times the square root of 2, roughly 2.828, which physicists call the Tsirelson bound, after Boris Tsirelson, who derived it in 1980. Quantum mechanics can violate Einstein's classical limit, but it cannot climb past Tsirelson's. The reason lies in the mathematics of non-commuting observables. Square the CHSH operator, and it equals 4 times the identity plus a term built from the commutators of the measurement operators on each side. A term that is bounded and whose bound caps the whole expression at 2 root 2. In plain words, quantum correlations get an extra push beyond the classical ceiling, but that push is itself limited by how much the measurements interfere with one another. The world is non-local, but not maximally so. And here is what makes that limit haunting. Nothing in the pure logic of no signaling requires the ceiling to sit at 2.828. Physicists have described hypothetical objects called Popescu-Raulich boxes. Imagine systems that would push the CHSH value all the way to its algebraic maximum of 4. Correlations far stronger than quantum mechanics allows, and yet still forbid faster-than-light signaling. Such boxes are perfectly consistent with no signaling. They are simply not how our universe is built. Consider what that means. The universe could, in principle, have been more non-local than it is, without ever permitting a message to cross. Instead, it stops precisely at 2 root 2. What does it mean that nature chose a level of connection stronger than the classical world and ours, weaker than no signaling permits, and pinned exactly to the structure of quantum mechanics? That number is a clue we do not yet know how to read. The reality of these correlations is not merely philosophical furniture. It has become a working technology. Anton Zeilinger's group demonstrated quantum teleportation in 1997, transferring the complete quantum state of one particle onto another distant particle, using a shared entangled pair and an ordinary classical channel to carry the 2 bits of correcting information. Notice the shape of it. The state crosses, but only because a sublight message rides alongside to complete the transfer. The no signaling principle is honored even in teleportation. And from the loophole-free Bell violations has grown device-independent quantum key distribution. Cryptography whose security rests not on trusting the hardware, but on the observed violation of Bell's inequality itself. The Messier satellite team pushed entanglement-based key distribution over 1,120 kilometers, removing the need for trusted relay stations. The strangest feature of nature, correlation without communication, has become a tool for building communication no eavesdropper can break. This is the part that stays with me. Einstein reached for a flaw and found a foundation. The connection he called spooky is real, confirmed past 22 standard deviations, woven perhaps into the geometry of space itself, and still, by the quiet arithmetic of no cloning, it will not carry a single word faster than light. The universe connects everything instantly. Signals cannot follow. Rest tonight inside a cosmos threaded with a link that is real, immediate, and mute, binding every entangled thing across whatever distance divides it, carrying no message, and perhaps, if the deepest conjectures hold, holding space itself together. Good night.